The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Let's get going here. Remember where we were? We were trying to figure out the structure of the atom at the beginning of the course. We saw classical physics, classical mechanics fail to describe how that electron and the nucleus hung together. So then we started talking about this wave-particle duality of light and matter. We saw that radiation and matter both can exhibit both wave-like properties and particle-like properties. And it was really important, this observation of Davison and Germer and Thomson, George Thomson, this observation that electrons exhibited interference phenomena. That is, when you took electrons and you scattered them from a nickel single crystal, the electrons scattered back as if they were behaving as waves. There were diffraction phenomena or interference phenomena, light, bright, dark, bright patterns of electrons. Okay? And and actually that Davison and Germer paper is on our website. You can welcome to take a look at that. But it was just that observation coupled with de Broglie's insight into Schrodinger's relativistic equations of motion that led Schrodinger to say, well, you know, maybe what I need to do is I need to treat the electron in a hydrogen atom. I need to treat the wave-like properties of that electron in a hydrogen atom. Maybe that's the key. In particular, maybe that's the key because the electron has a de Broglie wavelength that's on the order of the size of its environment. Maybe in those cases, I need to treat the particle as a wave and not as a particle with classical mechanics. Right? So he wrote down this wave equation, an equation of motion for waves, this H psi equal E psi, where we said last time we're going to represent the electron, our particle, by this psi, this wave. We're going to call it a wave function because we're going to put a functional form to it very soon. And there was some kind of operator here called the Hamiltonian operator that operated on this wave function. And when it did, you got back the same wave function times a constant E. And this constant, as we're going to see, is going to be the binding energy of the electron to the nucleus. All right, but then we took a little detour, and I said, well, let's see if we can derive, in a sense, the Schrodinger equation. And that's what we started to do. And I'm doing this, and I'm really doing this for fun. You're not responsible for it, but I'm doing it because I want you to see just how easy this is. Okay? Okay, so to illustrate this, I'm just going to take a one-dimensional problem. Right? I'm going to let my electron be represented by this wave, one dimension, psi of x, 2a cosine 2 pi x over lambda. And then I said, suppose I want an equation of motion. I want to know how that psi changes with x. Well, you already know that if I take the derivative of psi with x, that's going to tell me how psi changes with x, and we did that last time. And then I said, well, then I want to know the rate of change of psi with x. So I'm going to take the derivative again. So I have the second derivative of psi of x, and that's what we got last time. And then I noticed that in the second derivative, and you noticed too, somebody said this was recursive, that we have our original wave function back in this expression. So I can rewrite that whole second derivative here just as minus 2 pi squared, quantity squared over lambda psi of x. All right, so far, this is just any old wave equation, right? Nothing special about this. This anybody could and had written down before. But what's special is that Schrodinger realized here that if this is going to be a wave equation for a particle, then maybe this lambda here, maybe I ought to put in for lambda what de Broglie told me, and that is h over p. Maybe this lambda here is the wavelength of a matter wave. So let me write this expression in terms of the momentum of the particle, where the momentum has this mass m in it. And so when he did this, this became minus p squared over h bar squared. We said h bar is h over 2 pi times psi of x. All right. Hey, this is getting good because now we got a psi of x over here. All right. But then what he did is he said, well, I want to write this momentum. I want to write it in terms of the total energy. Total energy is always kinetic plus potential. The kinetic energy, we said the other day, can be written in terms of the momentum. The kinetic energy is p squared over 2m. And plus the potential energy, and I'm going to make this as a function of x, the potential energy. All right? So now I'm just going to solve this for p squared. All right? So p squared is equal to 2m times the total energy minus this potential energy. And now I'm going to plug this into here, right in there. All right? And when I do that, I'm going to get the second derivative of psi of x with respect to x equal minus 2m over h bar squared times e minus u of x times psi of x. All right, just simple substitution for p squared there, nothing else. And now I'm going to do some rearranging. And the rearranging is I'm going to, on the right-hand side, have only e times psi of x. E times psi of x, hey, that looks like the right-hand side of the Schrodinger equation as I wrote it down. Right? So that's good. So when I rearrange this, I get minus h bar squared over 2m times the second derivative of psi of x with respect to x plus u of x times psi of x equal e times psi of x. All right? And now I'm going to pull out a psi of x here. So that's minus h bar squared over 2m, second derivative with respect to x, plus u of x, the quantity times psi of x, equal e times psi of x. And guess what? We got it. All right? We got it because all of this, right, all of this is what we define as the Hamiltonian. All of this is h hat. H hat operating on psi of x gives us e times psi of x. All right? This Hamiltonian, as you will learn later on, this is a kinetic energy operator. This is the potential energy operator operating on psi. That's the Schrodinger equation, right? It's hardly a derivation. It's taking derivatives. It's a wave equation. The insight came right here. The insight is this substitution of the de Broglie wavelength in an ordinary wave equation. It's in an ordinary wave equation, right? This is the insight, is getting that momentum in there with the mass, making this then an equation for a matter wave. All right? That's it. Okay. So you just, quote unquote, derive the Schrodinger equation. Yay. All right. So, easy. All right. Now, So, bottom line here is that the Schrodinger equation is to quantum mechanics, like Newton's equations are to classical mechanics. When the wavelength of a particle is on the order of the size of its environment, the equation of motion that you have to use to describe that particle moving within some potential field, u of x, or u, you have to use this equation of motion and not Newton's equations. Newton's equations don't work to describe the motion of any particle whose wavelength is on the order of the size of the environment. All right? It just doesn't work. Now, just as an aside, classical mechanics really is embedded in quantum mechanics. That is, if you took a problem and solved it quantum mechanically, and you solved the problem, a problem for which the wavelength of a particle was much, much greater than the size of the environment, which is the classical limit, quantum mechanics would give you the right answer, right? In other words, say you took some problem where the wavelength of the particle is larger than the size of the environment. That's a problem where you would normally use classical mechanics. But if you use quantum mechanics, you would get the right answer if you could solve the problem. The equations are very difficult, but in principle, you would get the right answer. However, if you took a quantum mechanical problem, that is a problem where the wavelength of the particle is on the order of the size of the environment, and you use classical mechanics, well, you won't get the right answer, right? Because kind of classical mechanics is, in a sense, a subset. It's contained within quantum mechanics, all right? It's a limit of quantum mechanics, all right? So we have to learn a new kind of mechanics here, this mechanics for the motion of waves. Okay. So now, for a hydrogen atom, we have to think of the wave function in 3 dimensions instead of just 1 dimension here. And so we're going to have to describe the particle in terms of 3 position coordinates. Usually you use Cartesian coordinates, x, y, and z, but this problem is soluble exactly if we use spherical coordinates. So how many of you have had spherical coordinates before and know what we're talking about? Okay, not everybody, right? Okay. All right, so if I gave you an x, y, and z for this electron in this atom where the nucleus was pinned at the origin, if I gave you an x, y, and z coordinate, you'd know where that electron was. But alternatively, I could tell you the position of this electron using spherical coordinates. That is, I could tell you what the distance is of the electron from the nucleus. I'm going to call that r. That will be one of the variables. I could then also tell you this angle theta. Theta is the angle that r makes from the z-axis. That's the second coordinate. And then finally, the third coordinate is phi. Phi is the angle made by the following. If I take the electron and I drop it perpendicular to the xy plane, right, and then I draw a line here, well, the angle between that line and the x-axis, that's the angle phi. So instead of giving you x, y, and z, I'm just going to give you r, theta, and phi in spherical coordinates, all right? And now, this wave function is also a function of time, and I'll talk about that a little bit probably next time. All right, so that's the wave function that is in some way going to represent our electron. I haven't told you exactly yet how psi represents the electron, and I won't tell you that for another few days. Question?
Yeah, in math,
yeah.
Uh-huh. And theta is in the xy plane.
Okay.
Is that different?
No, it will just I actually thought this is the way the book set it up, but I may have it backwards.
From my experience, chemistry does it backwards.
Right, right. I think this is the way our book does it, sets it up. So let's see, it won't make a difference in any of the problems we solve here, but in general, if you're given a problem to solve, you're going to have to look and see how they define their coordinate system. Okay? Okay. Actually, somebody else asked me that the other day. Right, right. Okay. All right, so now what we've got to do is we actually have to set up the Hamiltonian for the hydrogen atom. That is, we have to set up the Hamiltonian specifically for the hydrogen atom. And we've got to set it up in terms of spherical coordinates, r, theta, and phi. And when we do that, and we're not actually going to do that, but when we do that, that's what the Hamiltonian looks like. Okay? Yeah. And actually, you know, this is in 3 dimensions, and so if I were doing it in the x, y, z, what I would have here is a second derivative with respect to y plus a second derivative with respect to z. All right? That's what it would look like in 3 dimensions in Cartesian coordinates. But when I transform from Cartesian coordinates to spherical coordinates, and that's an exercise which takes 5 pages, and everybody should have that experience once in their life, but maybe now is not the right time for that experience, you do get this, okay? And essentially what this is, the Hamiltonian, is a sum of second derivatives with respect to each one of the coordinates, because essentially this term, hey, that's a second derivative with respect to r. This term's a second derivative with respect to theta. This term's a second derivative with respect to phi. All right? So that's the specific Hamiltonian. These are all kinetic energy operators, as you will learn later on. And then there's this term here, U of r. Hey, this U of r, what is that? What is U of r? Potential energy, right? It's the Coulomb potential energy of interaction. It is isotropic, meaning it's the same at all angles. The only thing it depends on is the distance of the electron from the nucleus. It only depends on r. It doesn't depend on theta and phi. Okay. All right, so that is the Schrodinger equation for the hydrogen atom. All right, it's a differential equation, second order ordinary differential equation. In 1803, you're going to learn how to solve that. In 561 or 804, I think it is in physics, in quantum mechanics, you're going to solve that. You can do that. It's not hard. Okay. But what do I mean when I say solve? What I mean is that we're going to calculate these E's, these binding energies, this constant in front of the psi. That's called an eigenvalue for those of you who might know something already about these kinds of differential equations. This E here, it's the binding energy of the electron to the nucleus. We're going to look at those results in just a moment. And the other quantity we're going to solve for here is psi. What we're going to want to find is the actual functional form for the wave functions. That we can get out of solving this differential equation, right? The actual functional form for psi. The functional form is going to be more complicated than what I wrote here, right? Okay, but we can get that, and we'll look at that in a few days from now. And those wave functions, hey, you know what those wave functions are? Those wave functions are what you studied in high school as orbitals. You talked about an s orbital, p orbital, d orbital. Hey, orbitals are wave functions. That's where they come from, orbitals, from solving the Schrodinger equation. Now, specifically, orbitals are the spatial part of a wave function. There's also a spin part to the wave function. But for all intensive purposes, we're going to use the term orbital and wave function interchangeably, because they're the same thing. Okay? Question?
How is binding energy different from like a work
Okay, we're going to get to that in just a moment, okay? Then I'll come, if you think I don't answer it, then we'll go back to that, okay? Okay, so we're going to solve this. We're going to, and this equation is going to predict binding energies, and it's going to predict these wave functions in agreement with our observations. And it's going to predict that the hydrogen atom is stable. Remember when we tried to predict the hydrogen atom using classical ideas? We found it lived a whole whopping 10 to the minus 10 seconds. Not so when we treat the hydrogen atom with the quantum mechanical equations of motion. Right? Okay, so let's write down the results for solving the Schrodinger equation. And the part I'm going to concentrate on today are these binding energies. And on Friday, we'll talk about the wave function, solving the Schrodinger equation for those wave functions. Okay, so let me put this up. So, what does the binding energy look like? Well, the binding energies here, coming out of the Schrodinger equation, look like this: minus 1 over n squared times m e to the 4th over 8 epsilon naught squared times 8 squared. M is the mass of the electron. E is the charge on the electron. Epsilon naught is this permittivity of vacuum we talked about before. This is a conversion between ESU units and SI units. H, Planck's constant. Planck's constant is ubiquitous. It's everywhere, right? What we typically do is we lump these constants together. And we call those constants a new constant. We call it the Rydberg constant, R sub h, right? And so our expression is equal to minus 1 over R sub h over n squared. The value of R sub h here, the value of R sub h is equal to 2.17987 times 10 to the minus 18 joules. All right, that's a number that you're going to use a lot in the next few days. All right, but what you also see here is an n. What's n? Well, n is what we call the principal quantum number. And its allowed values are integers, where the integers start with 1, 2, 3, all the way up to n is equal to infinity. Okay. Well, let's try to understand this a little bit more by looking at an energy level diagram again. And, okay, we need to turn, okay, good. All right, so I'm just plotting here energy. Here's the zero of energy, right? Here's the expression for the energy levels that come out of the Schrodinger equation. So when n is equal to 1, that's the lowest allowed value for n, binding energy is essentially the Rydberg constant, equal to minus the Rydberg constant, right? But our equation says the binding energy of the electron can also be this value, because when n is equal to 2, well, the binding energy now is only a quarter of the Rydberg constant. It's higher in energy. When n is equal to 3, well, the binding energy of that electron to the nucleus is 1/9 of the Rydberg constant. When it's equal to 4, it's 1/16. When it's equal to 5, it's 1/25. When it's equal to 6, it's 1/36. So on, so on, so on, until it gets n equal to infinity. When n is equal to infinity, then the binding energy is 0. When n is equal to infinity, the electron and the nucleus are no longer bound. They're separated from each other. They don't hang together when n is equal to infinity. Now, this is rather peculiar. This is saying that the binding energy of the electron to the nucleus can have essentially an infinite number of values, except it's a discrete number of infinite number of values, right? In the sense that the binding energy can be this, or this, or this, but it can't be something in between here, or here, or here, right? This is the quantum nature of the hydrogen atom. There are allowed energy levels. Where did this quantization come from? It came from solving the Schrodinger equation, all right? When you solve a differential equation, as you will learn, and that differential equation applies to some physical problem, in order to make that differential equation specific to your physical problem, you often have to apply something called boundary conditions to the problem. When you do that, that's when this quantization comes out. It drops out of solving the differential equation. What are boundary conditions? Well, remember I told you in the spherical coordinate system, r, theta, phi. Well, phi, sweeps from 0 to 360 degrees. Well, if you just went 90 degrees further, so if you went to 450 degrees, well, you really have the same situation as you have when phi was equal to 90 degrees, right? All right, so what you have to do in a differential equation, which usually has a series as a solution, is that you have to cut it off. You have to apply boundary conditions. You have to cut it off at 360 degrees, because otherwise you have the same problem that you had before. This is a cyclical boundary condition. And it's that cutting it off to make the equation be really pertinent or apply to your physical problem. That's what leads to these boundary conditions mathematically. All right? That's where it comes from. That's where all the quantization comes from. All right. So now let's talk a little bit about the significance here of these binding energies, because somebody actually asked me about it already. When the electron is bound to the nucleus with this much energy, we say that that electron is in the n=1 state. Or equivalently, we say that hydrogen atom is in the n=1 state. We use both kinds of expressions equivalently. When the hydrogen atom or the electron is in the n=1 state, we call that the ground state. The ground state is the lowest energy state. The electron is most strongly bound there. The binding energy is most negative. And the physical significance of that binding energy is that it is minus the ionization energy, right? Or alternatively, the ionization energy is minus the binding energy. It's going to require this much energy from here to here to rip the electron off of the nucleus, right? So the ionization energy here is, the binding energy here is minus the ionization energy. That's the physical significance of it, all right? Now, I think, did you ask me about the work function?
How is it different or the same as the work function?
Okay. The work function is the ionization energy when we talk about a solid, all right? That's just a terminology. That's historical. So when we talk about ripping an electron off of a solid, we call it the work function. When we talk about ripping it off of an atom or a molecule, we call it the ionization energy, right? And the other important thing to note here is that when we talk about an ionization energy, we are usually talking about the energy required to pull the electron off when the molecule or the atom is in the lowest energy state, the ground state. All right? That's also important. Okay. But our equations tell us we also can have a hydrogen atom in the n equal 2 state, right? If the hydrogen atom is in the n equal 2 state, it's in an excited state, and actually it's the first excited state. The electron is bound less strongly, right? It's bound less strongly, and consequently the ionization energy from an excited state hydrogen atom, that ionization energy is less because the electron isn't bound so strongly. And of course, we could have a hydrogen atom in n equal 3 and n equal 4 and n equal 5. Any of these allowed energy levels. Not all at the same time, but in any given time, if you had a lot of hydrogen atoms, you could have hydrogen atoms in all of these different states. Okay, now, the other point that I want to make is that this Schrodinger result here for the energy levels predicts the energy levels of all one-electron atoms. What's a one-electron atom? Well, helium plus, that's a one-electron atom or a one-electron ion, right? Helium plus, helium usually has 2 electrons, but if we pull one off, it's only got 1 left, so it's a one-electron atom. Lithium double plus is a one-electron atom because we pulled 2 of its 3 electrons off. Hey, 1 electron's left, that's a one-electron atom or an ion. Uranium plus 91, hey, that's a one-electron atom, right? We pulled 91 electrons off, we got 1 left, hey, that's one electron atom. The Schrodinger equation will predict what those energy levels are as long as you remember the z squared up here, right? For hydrogen, z is 1, and so it doesn't appear, but z is not 1 for all of these other one-electron atoms. Where does the z come from? It comes from the Coulomb interaction. The potential energy of interaction is the charge on the electron times the charge on the nucleus, which is z times e. That's where the z squared comes from. So you have to remember that. All right, so now, how do we know that the Schrodinger's predictions for these energy levels are correct, are accurate? Well, we got to do an experiment. So the experiment we're going to do is we're going to take a bulb here, pump it out, and then we're going to fill it up with hydrogen, molecular hydrogen. And then in this bulb, there's a negative and a positive electrode. And what we're going to do is we're going to crank up the potential energy difference between those two so high until finally that gas is going to ignite, just like that. All right? And we're going to look at the light coming out. And what we're going to do is we're going to disperse that light. We're going to send it through a diffraction grating, essentially. And that's like an array of slits. And what you're going to see are points of constructive and destructive interference. But in the constructive interference, you're going to see the colors separated. So there's going to be purple, blue, green, etc. And the reason is that the different radiation, the different colors have different wavelengths. They have different wavelengths, then they have slightly different points in space at which constructive interference occurs, and so the light is dispersed, right, in space. So we're going to analyze what are the wavelengths of the light that are being emitted from these hydrogen atoms. See, the discharge pulls apart the H2 and makes hydrogen atoms. All right? So we got to do this by taking a diffraction grating, and the TAs are going to give you a pair of diffraction grating glasses. You're supposed to come and look at the discharge here. You can see it. I'll turn it a little bit for those of you on the sides here. And we'll see what we see. Okay, sorry. And if you can't see the lamp, you're welcome to get up and move around and so that you can see it. Thank you. Can you do this light too? This one over here, sir? Can you move this one away? All right. Okay. And if you look up at the lights in the room, you can see the whole spectrum, right? Because that's white light. So, I'm going to turn the lamp over here so that you can see this a little better. All right? The spectrum that you should see is what's shown on the board. If you look to the right of the lamp here, you should see a purple line. The purple line is actually very light. So only if you're up close are you going to see the purple line. You can see the blue line very well. That's very intense. The green line is also very diffuse. So again, only if you're up close are you going to be able to see the green line. And then the red line's very bright. And now I'm going to move this over here so you have the opportunity to see it. And again, you're welcome to get out of your seats and move around so that you can, in fact, see it. Okay? All right. So what you should be seeing, and now if you look... Hey, interference phenomena works, huh? Useful pointer.
I can't tell which one I'm pointing.
No, right. Okay. So what you should see, depending on which one of the constructive interference patterns you're looking at, there should be the purple line, right? There should be a blue line, very intense. Purple's weak. Green is rather weak. And the red is very intense. All right. So what's happening here? Well, what's happening is that in this discharge, there's enough energy in that discharge to put some of the hydrogen atoms in a high energy state. And we'll call that state E sub I, the energy of the initial state. And actually, that's an unstable situation. There's that hydrogen atom wants to relax. It wants to be in the lower energy state. And what happens is that it does relax, right? It relaxes, right? The electron falls into the lower energy state, but because it's lower energy, it has to give up a photon. And so the photon that is emitted, the energy of that photon has to be exactly the difference in energy between the energy of the initial state and the final state, right? That's the quantum nature of the hydrogen atom. The photon that comes out has to have that energy difference exactly. And therefore, the frequency here of the radiation coming out is going to correspond to that exact energy difference. All right? And for the different energies, for the different transitions, you're going to have very specific values of the frequency of the radiation or the wavelength of the radiation. So for example, some of those hydrogen atoms in this discharge, they've been excited to this excited state, which we'll call B. The energy difference between B and this ground state here is small. Therefore, we're going to have some radiation that is low frequency because delta E, the difference in the energy between the two states, is small. And then there are going to be some hydrogen atoms that are going to be excited to this state, the A state. And relatively speaking, that energy difference is large. So there are going to be some hydrogen atoms that are going to be relaxing to this ground state. And when they do, since that energy difference is large, the frequency of the radiation coming off, it's going to be high. Or correspondingly, the frequency of the radiation, the wavelength of the radiation coming off is going to be low because the wavelength is inversely proportional to the frequency. And likewise, for this transition, we're going to have some long wavelength radiation emitted. All right, well, let's see if we can understand specifically the spectrum here in the visible range for the hydrogen atom. So what I've done is to draw an energy level diagram again. Here's the energy of n equal 1, n equal 2, n equal 3, etc. Here's the n equal infinity up here. All right, so it turns out that this purple line, that's a transition from a hydrogen atom in the n equal 6 state to the n equal 2 state. That blue line is a transition from n equal 5 to n equal 2. The green line is a transition from n equal 4 to n equal 2. And the red line from n equal 3 to n equal 2. Notice that since this energy difference here, since this energy difference is small, right, this line has a long wavelength. Since this energy difference is larger, this line has a shorter wavelength. So all of these transitions that you're seeing in the visible range, all of these transitions have the final state of n is equal to 2. Now, how do we know that the Schrodinger equation is making predictions that are consistent with the frequencies or the wavelengths of the radiation that we observe here? Well, we got to do a plug here. This is the frequency that we would expect. It's the energy difference between two states over h. Here's the initial energy, here's the final energy. We said that the Schrodinger equation tells us that the energies of the state are minus r sub h over n. So for the initial energy level, it's minus r sub h over n sub I squared. We plug that in. For the final energy level, well, it's minus r sub h over n sub f, the final quantum number squared. We plug that in. We rearrange some things. And then this is the prediction for the frequency. I said that this level right here is the n equal 2 level. So we'll plug in the 2 for the final quantum state. And so this is then the prediction for the frequencies of the radiation to the n equal 2 level. And so you just plug in n equals 6, n equal 5, n equal 4, n equal 3, and you know what? The frequencies that are predicted match what we observe to 1 part in 10 to the 8th. There really is precise agreement between the results of the Schrodinger equation and what we actually observe in nature. Therefore, we think it's correct, right? And there are no experiments that cast any doubt so far on the Schrodinger equation, all right? Okay. Now, the set of transitions that we just looked at are these transitions. Plotted here is another energy level diagram for the hydrogen atom. Here's the n equal 1 state, n equal 2, n equal 3, n equal 4. Right? And we looked at all of the transitions that end up in the n equal 2 state. This set of transitions, it's called the Balmer series. Now, the n equal 2 state is not the ground state. Right? There is a transition from n equals 6 to n equal 1, the ground state. It's this one right here. But you see, that's a very high energy transition. Actually, this transition from n equals 6 to n equal 1 is in the ultraviolet range of the electromagnetic spectrum, and so you can't see it with what the experiment that we did, but it's there. And then, of course, the hydrogen atoms that relax to n equal 2, well, they actually eventually relax to n equal 1, and there is a transition there. It's over here, n equal 2 to n equal 1. But again, that's a high energy transition. It's also in the ultraviolet range of the electromagnetic spectrum. And so all of these transitions that end up in n equal 1 are in the UV range. They're called the Lyman series. All the transitions that end up in n equal 2 are in the visible. They're called the Balmer. N equal 3, the Paschen, and the infrared. Bracket is in the infrared. Fund is in the infrared. Okay? And so we can't see these easily. Now, these are named for the different discoverers. The reason there's so many different discoverers is because these are all different frequency ranges. Different frequencies of radiation require different kinds of detectors. And so depending on exactly what kind of detector the experimentalist had, that will dictate then which one of these sets of transitions he was able to discover. All right. But not only does this work for emission, but this also works for absorption. That is, we can have a hydrogen atom in the ground state, a low energy state, and if there's a photon around that is exactly the energy difference between these two states, well, that photon can be absorbed. If that photon is a little bit higher in energy, it won't be absorbed. If it's a little lower, it won't be absorbed. It has to be exactly the difference in the energies between these two states. Again, that's the quantum nature of the hydrogen atom. And now, if you're calculating the frequency for absorption, well, what I've done here is I've reversed n sub I and m sub f. So this is 1 over n sub I squared instead of 1 over n sub f squared, which was the case in emission. And I've reversed this so that you get a positive value for the frequency of the radiation absorbed. All right, so we'll have two different equations for absorption and for emission. Okay, so those are the Schrodinger equation results. I forgot to announce there's a forum this evening from 5 to 6. Should have signed up in recitation. If you didn't and still want to come, send us an email and come. And we need the diffraction glasses back as you're exiting. Okay, see you Friday.